All right, so let's talk about 101 plus. Could have done 1001. I don't know, as many as you want. Projectile problems. If you want to master this, then think like an expert. You realize that the essential physics is always the same. The essential physics is that when we say a projectile problem, we inherently mean, especially in introductory physics, that we're talking about what I call free flight. Most people call it free fall. Just realize that in flight, I'm not talking about any propulsion. And if we say fall, that includes going up. So while this is going up, it's falling. And while it's coming down, it's falling. So that's what you can use free fall or free flight either way. I like the FF. So negligible area effects, no curveballs, no tennis, no soccer balls, no volleyballs, no baseballs, curving, so no air effects, or negligible. So a free fall, as you know, or free flight, is a vector. It has a direction down, which could be, it's going to be down. Now you can call that plus, or you can call that minus, and we'll talk about it. It has a magnitude of g, which you know what that is, 9.80 meters per second every second, or meter per second squared, or 9.81 or 9.79, whatever it turns out to be you work with. But g is not gravity. People sloppy might say gravity. It's not gravity. It's the acceleration due to gravity. Remember, as a reminder, acceleration does not cause a change in velocity. Acceleration describes the rate at which velocity is changing. What's causing it is coming next in the next chapter. What's causing it, we'll see, is the net force, all the interactions. But this is just describing the rate at which it slows down on the way up and speeds up on the way down. Decreases speed, increases speed, maybe a better way to say it. Okay, so in general, for problem solving, we know our method. Do a quick read, do it. It's different if you do it than if you don't. Then you slowly sort out all the information. This is key. You've got to visualize and sketch, right? So what are the key states? What are the coordinate choices? Show them. It's going to save you a lot of time. And show all your variables. Now, you might be able to show it all there on the sketch. You might not need to list it in the given implied want. But the implied part here is what I want to look at really today. Then, once you do that in a problem, you need your general methods. We've got kinematics, we'll have Newton's laws, we'll have momentum, we'll have energy, things like that. So you write those general relationships down. Then you fit it to the problem at hand. Then solve, then do the math. That's not, up here, this is where it's at. That's just algebra, so you should be able to do that, of course, and practice is important. Analyze your results. Do they make sense? What do they tell you? Repeat if needed. So in projectile problems, we know the general method is going to be, right now, kinematics. So if I apply kinematics to this, it's two-dimensional. I know that the general relationship, I can take the general constant acceleration equations. I can fit them to a general projectile problem and say, hey, horizontally, there's no slowing down or speeding up, no propulsion, no air resistance here. Put those in there, and all you're left with is one equation. So you should be able to do that. This should not be a memorization. You should be able to go back there and just go, oh, acceleration 0, I see that. I get this. This is my displacement, horizontal, from any earlier to any later state, any two that you need. You need some other two, write the equations again. Vx, which never changes because the acceleration is 0. So if you have the x component of velocity at the start, you've got it everywhere. You've got it right before it lands, you've got it at the top, you've got it everywhere. It's the same. Keep that in mind. And then, of course, the time between those two states. In the y direction, we have our choice. If you call plus y up, then ay is negative g. If you call plus y down, then ay is positive g. And we'll talk about that in a minute. So then delta y earlier to later is the earlier y component. Delta t plus, actually I should flip that. If I choose up positive, then let's be consistent there. Minus for up positive, positive for down positive. V later y is V earlier y minus plus V later y squared is V earlier y squared minus plus in this case. Anyway, you hopefully get that. 2g delta y. So what you need to look at are the vectors, because the vectors have components. And in these equations, the vectors that have components are going to be displacement x, displacement y. You just need to see on your picture where they are. And be careful of your sign, plus or minus. Be really careful. That's where people mess up, and it frustrates, and you get tired, and you go eat a pizza. So there's displacement, and there's velocity x, and velocity y, which, as you know, on the way up decreases speed, and on the way down increases speed. So velocity y is changing. You divide and conquer, just like we did with vectors. So that's what you've got. Acceleration, we know the gig there, so that's it. So let's take a look at here at any particular problem. The results will sort themselves out, and it'll lead you to thinking more intuitively, conceptually about what's going on. So I've drawn this twice, a general projectile problem. Okay? So I'm going to shoot the ball up, throw the ball up, whatever it is. While I'm throwing it, of course, there's a different acceleration. The acceleration is not g, right? It's due to my hand, and there's a force of gravity, whatever. But the moment I let go, until the moment just before it hits something, it's in free flight. So I've drawn it both ways. Let's look at velocity first. So you need to have an awareness. The good news is that you're just going to use this between any two states. Now, I'm going to name these states. I'm going to name them, I think, here in my blue. Actually, I'll use green. I like to start with 1. You could start with 0. I don't like initial and final because there's lots of states. There's state 1. There's state 2. State 3, which, by the way, is the top of the path. State 4, state 5, state 6. You could have as many as you want. And those correspond with the ones below it. So now, the question is, okay, what is the velocity in the x direction, and what's the velocity in the y direction? So you guys see, at each moment, we need to draw the velocity vector. This is a key point. Make sure you get it. It's not hard. Get this. The velocity is always tangent to the path. Always. That's where you're going at that moment. Always tangent to the path. It does not connect the states. It's just at that moment, it's going there. At that moment. But it is changing. Okay. So that would be V2, V3, V4, V5, V6. Velocity vectors are always tangent to the path at that moment. It doesn't mean you aren't changing direction. It just means that at that moment, that's your velocity. Not a very good one there, but we'll do our best. Okay, now, so we need to think in terms of components. So, for example, make your list. Let's talk about Vx and Vy at different states. So let me go over here, and let me try to not go too crazy, but I'm going to go Vx and Vy at the different states. 1, 2, 3, 4, 5, 6. What do I have? Let's take a look at that. So you need to be able to see. Let's look at Vx. Vx here. I like to do dashed lines for components. So V1x is equal to, a lot of books and a lot of folks don't subscript the angle. I think that's a mistake. Just subscript everything. That angle is changing. So that's the angle with the horizontal at state 1, theta 1. So how much is it? Well, it's up V1 cosine theta 1. But now wait a minute, I don't know whether I've called up positive or negative. So it could be either one. Personally, if it goes up at all, I call up positive. And so, but I'm in trouble if I don't, again, make a note of this. So on my problem, let's do this right now. I'm going to put plus y, and next to the coordinates, ay is equal to negative g. Plus x, ax equals 0. Writing that will make you faster and avoid mistakes. And we're going to build on that when we do Newton's laws too, in a big way. So now I can say that's positive V1 cosine theta 1. Now remember, I might not know that. Some of this is going to be known through experimental measurement, or it's just given in a problem, and the rest you find out. And that's the game. Okay, so if it's not known, fine, just leave it as a symbol. Okay, so then I look here and I've got V2x. And here, hey, wait a minute. That's V3x. And here, V4x. And here, V5x. And here, V6x. And what do we know about Vx? It's always the same. Find it anywhere you can, and you have it everywhere. And so, for example, here it's positive V1 cosine theta 1. And it's the same, it's the same, it's the same, it's the same. What do you know about V3x, guys? Gals? Guys means gals into it. What's V3x? It's the same as V1x, but there's something else. V3x is V3. Right? At the top, at that moment, it's all going horizontally. So here's a little kind of thing to throw in here. Hey, V3x, which is the same as this, is equal to V3 at the top. This is top. Okay, cool. So you just have to be aware of that because you're going to fit it into the problem. All right, any questions about Vx? We're dividing V. It's a vector. We need to divide and conquer. Cool. Let's do now Vy. So look at Vy, and let's do this. Let's do it in green, I guess. I don't know, pink. Let's try pink. Vy. There's V1y. And remember, you can throw it up, you can throw it horizontally, or you can throw it down. You can throw it straight down, you can throw it straight up, you could drop it. These are all, they all fit in here. You just have to look at these parts. What do you know? Here's V2y. Is it the same as V1y? No. What do you know about V3y? It's 0. V3y is 0 at the top. That is implied information that no one's going to tell you because they expect you to know that. In this case, V1y is equal to what? Positive or negative? Positive V1 magnitude sine theta 1 angle from the horizontal. Maybe I know it, maybe I don't. But that's what goes in here if state 1 is your earlier state. Remember, you can choose any of these and write these equations. You can fit these equations, so you might say, hey, I want to do 1 to 2. Now I want to do 1 to 3. Maybe I want to do 3 to 6. Okay, there's going to be some other interesting things in a moment. So hopefully you get this. You can see, though, that v, y, it's decreasing speed on the way up. It stops. v3y equals 0. And then it increases, and increases speed on the way down at a rate of g. So we've got that. Okay? So you can do these. And then they're negative or downward down there. Okay, so now let's look at displacements. And this is the key. This is the missing piece that people always go, I don't have enough information, or I don't know, they get stuck. Because just quickly identify the states you want and do this. Let's go here again. 1, 2, 3, 4, 5, 6. And let's talk about our delta x. Now this is tricky. I'm going to start from 1 to a later state. And delta y, 1 to a later state. People mess this up. All right. So I can go 1 to 2. Delta x 1 to 2 equals. So where is that on my picture? Here to here. Delta x 1 to 2. Okay, so you see it. Where is, and again I like to do dashes for my components, where's delta x 1 to 3? Well, it's just delta x 1 to 3. Now there's going to be some meat in here in just a second. So you want to know how far you went sideways to get to the top. This is still the top. Well, that's it. How does it work out? I don't know. We'll fit all our information into our method and see how it works. Another real useful one is this, and we'll see that. Delta x 1 to, what did I call that? 5? Yeah. And sometimes we call that the range. Okay, and you'll see the range equation, which you can memorize if you want, but you have to be able to derive that, and we'll see it just comes out of here. It's one of many, many 101 plus problems. Okay, now also, by the way, you could do, what's this? What's here to here? Delta x 3 to 5, which is equal to what? Delta x 1 to 3. Right? So that's interesting. So you have to bring that awareness to your picture. Delta x 1 to 3 is equal to delta x 3 to 5. And so just write that, because you're just going to fit it in here and do the algebra. That's going to be the easy part, but getting this in here is going to be tricky. No, we don't have time. 1 minute. Okay, so delta y, quick. Delta y. Well, where's delta y? Delta y, is that positive or negative? Delta y 1 to 2 is positive in this case. What about delta y 1 to 3? 1 to 3. So delta y 1 to 3 is positive. What about delta y 1 to 4? Where's that? It's just this. You don't have to do the path. It's just delta y 1 to 4 is from here to here. What's delta y 1 to 5? That's critical. If you want to find the range, you just have to realize that in this picture, delta y 1 to 5 is 0, and that makes your math so easy. It's a piece of cake, and yet it gives people trouble. What about delta y 1 to 6? It's negative. It's from here down to here. You don't care about the path. It's displacement. Delta y 3 to 6, it's from there down. 4 to 6, from here down. 4 to 5, from here down. So just see it. Know which states you want to relate.